Hello, my name is Bradley Alisea, and I'm here to talk about network. Hello, my name is Bradley Alisea, and I'm going to talk to you today about network architectures for growing academic open source. We're going to talk about three different organizations. The first is the Rokwire Initiative, which is an open source software community based at the University of Illinois Urbana-Champaign. The second is the Orthogonal Lab, which is an independent collaborative entity focused on research and education. And finally, the Open Room Foundation, a 501c that engages in software development and research. So all three of these different organizations I'm going to talk about today are sort of disruptive versions of an academic department. And so in this article from the early 70s, they talk about sort of the organizational model or the tradition of an academic department. And it's sort of a mix of democracy and oligarchy, but throughout it's defined by these strictly regulated and regimented rules for people. So keep that in mind. During COVID-19, which is one of these black swan events that people talk about, it took some of these organizations, these traditional organizations, and turned them on their head. And so you can see in this tweet, they talked about, Plo's headquarters on the day after everything shut down. And they were talking about how there were just 11 people in the office. And they were glad that people were staying well, but there was no one in the office. So there was a lot of sort of need for these virtual distributed communities that are robust to rare unforeseen events that adversely affected traditional institutions like the PLOS office or even like traditional academic departments. Now, as long as these enabling technologies are in place, these events can actually increase community activity. And that's what I'm going to be talking about with all three of these organizations that I previously mentioned are these virtual distributed communities. And we're going to talk a little bit about how they form networks. So during COVID, there was a lot of collective action around these technologies to form distributed virtual communities. And distributed virtual communities, such as the Orthogonal Lab, can leverage other initiatives, such as the Neuromatch Academy, and this builds this sort of ecosystem of these type of institutions. The question is, how are they connected together, and how are people sort of structured in their roles and in their sort of contributions? So I've written a preprint on this about the Orthogonal Lab. This is called Building a Distributed Virtual Laboratory Adjacent to Academia, and this is on the MetaArXiv. And in this preprint, I describe a number of attributes of the Orthogonal Lab that make it unique and that build off of the structure that we have. So we're a worldwide distributed lab. We have facilities everywhere and nowhere. We have people, different collaborators in different parts of the world. We collaborate using virtual tools such as Slack and Jitsi and other types of things like Google Docs and GitHub. And we're able to leverage this sort of interactivity to our advantage. We can edit things in real time and asynchronously. We can do the same with meetings. We can talk about things and also give talks and publish things in the same way. We have this global and virtual connectivity that brings people together from all over the world. So you can see we have people from India, we have people from North America, we have people from Europe, and they're all sort of interacting in different ways in these meetings, for example, but in other contexts such as paper collaborations or other types of events that we might host. So we have a number of initiatives in the Orthogonal Lab, and so one way we can take this structure is to build it around little projects and initiatives. And so we have all these initiatives in the Orthogonal Lab currently ongoing. And so one way we can organize this is looking at the network of collaborators, but another way we can understand this is looking at a network of these initiatives and how they're connected. So we can connect people based on their affinities, or we can connect initiatives based on their affinities. And so you can see we've built a network of affinities here between different initiatives. And these initiatives pop up as people are interested in participating in them. So you can see that there are ties between initiatives and there are selective ties between initiatives, but also, you could say weak ties between initiatives as well. And there's sort of a space of, a continuum of different topical areas that we cover quite effectively by using this type of organizational model. So before I move on to the next part of the talk, I want to talk about growing networks and institutional value. So this is something that was really kind of stressed at the beginning of the internet in the 1990s, but it's worth revisiting because I think in light of a lot of these organizations, this does give us some clues as to how this is valuable, how these networked approaches are valuable. So the first is Metcalfe's law, and that is where the network grows in value at a rate of end of the square growth per node added. So every time a node is added, there's a squared growth rate, as opposed to Reed's law, which is networks that grow at an exponential value of 2 to the n per node added. So every time a node is added, there's an exponential increase in the amount of value in that network. And so we can use both of these laws to kind of think about when we see these networks. And I'm going to show in the next few slides what the value of these networks might be. So this leads us to a question, and that is, how do we translate academic community building into the language of complex networks? And this is specifically with respect to individual connectivity, or the connectivity of individuals plugging themselves into the networks. But we have to back up before that and ask, what is the structure of networks for open source collaboration? So we recall that open source communities are transient, flexible, and hierarchical, which means they're not hierarchical. They have a number of different ways they can be structured. And so we have to keep that in mind. And so if we want to drill down on the hierarchy point, we can recognize that nodes can be ranked in a number of different ways. And so in our case, or in our 3 cases, aside from initiatives led by the project leader, there are numerous ways to become connected into and gain connectivity into a network. There's also a low barrier of entry into the network. And this means that preferential attachment rules and things like that are not generally applicable. Finally, the open source networks that we have in these communities have multiple functions and objectives, and we'll show what that looks like later. So quickly, we want to look at hierarchies versus hierarchies. Hierarchies are these star-shaped structures with a single node, single point of connectivity, whereas hierarchical structures are more diverse. And the same holds true for things like this, where you have hierarchies where you have people underneath other people, as opposed to a hierarchy where people are constantly exchanging information and exchanging leadership versus mentorship and things like that. So one thing we can pull out of these types of communities, one type of interaction, are these one-to-many interactions. So this is an example of a network structure in the OpenRPG community, and this interaction graph is based on bug reports. So it's using a single measure to yield this network topology. So keep that in mind before we move on, because that's going to become important later. And then, to bring up this point of hierarchy again, we do observe this sort of desirable trait in these open source communities, which is the reconfigurability of expertise. And that is that we want to be able to move people around to different tasks when needed. So let's say that we have a web design and maintenance task, which is a rolling task, happens every couple months. We can gather people in this loosely knit community into these groups that might do this sort of work. But say we want to then build a new module this summer onto our software. Well, we can get other people, maybe some of the same people, but other people as well, and recruit them for this task. And so you can see that there's this reconfigurability of expertise. You go from one group of people to another group of people, and you don't really have to recruit new people into the network. So we look at this structure again, and we recognize that the contributors are the nodes, and the strength of their contribution are the edges. And so we want to find the pathways to creating a sustainable community, and we can measure that through using statistical trends. So, one of our inspirations for this is to look at co-authorship networks. We can look at different types of networks where we have co-authorship between different collaborators and how they cite each other. We can also look at how they sort of collaborate through just collaboration networks, looking at how they exchange information between one another. So those are kind of our inspirations. And so this is the Rokwire community. And so the Rokwire community is interesting because it's located on a university campus. It's mostly operationalized virtually, but it's located on a university campus. And during COVID, of course, the campus was more virtual than it usually is. So the Rokwire community is sort of building upon that capacity. So this Rokwire community is a community network that is connected into the larger campus network. And so there's a need for network enrichment metrics for this type of community. In other words, how much do interactions in the community impact or enrich the adjacent academic community? And so one way we can do this is sort of think about a model here, which is which contributors and disciplines are your greatest source of contributor activity. So here we have a contributor from discipline A, and they're plugging into this network. And so the input of a contributor from discipline A, we have to ask the questions: what kind of niche expertise do they bring into the community? They might know a specific technique, or they might have a specific language that they know, a computer language that helps fulfill some of your goals. Do they act as a conduit? In other words, do they bring more contributors from discipline A? Maybe if they do, then that's great. If they don't, well, that's still okay, but we just want to know what that looks like. Finally, we have to consider the duration of a contribution, the intensity of contribution. What is their magnitude of their contribution history? Maybe they come from discipline A with a great number of skills. Maybe they only come with a niche skill. All of these are good, but we just want to know what that impact is. The second sort of signature that we want to look for are long tails, but we only want to look for those during certain modes of engagement. So I'm going to show you a couple of graphs, and they're going to be basically trying to investigate this long tail behavior in different communities. So I'm actually going to go to the Wikipedia community, and I'm going to look. The Wikipedians are people who contribute to Wikipedia, and by using their open source data set, we're able to look at the edits contributions. So these are people who have edited pages and done a lot of this type of work. And so there are a lot of Wikipedians, but there are only a certain subset that are heavy contributors to the Wikipedia platform. So this is the top 10 to the 4th contributors. This is their rank order, number of contributions. This is their log edit count. So you can see that it follows a sort of long tail pattern. But we want to look at this in terms not just of their overall contribution patterns, but what they're actually doing. And so in this case, these top 5 categories, we look at like the number of contributors per category. We see that there are also a larger number of contributions in certain categories than others. So we look at these top 5 roles, and we can see that it involves verification and administrative permissions. So this is indicative of building trust through demonstration, and we're utilizing a skill built through demonstration. So in other words, what's going on here is that people are coming into the network, they're doing certain types of things that are sort of like gateway activities, and they're able to build trust in the community. And so if they're doing a lot of this, or if there are a lot of if there are a lot of opportunities for this is interesting, because this tells us that this is kind of how they're connecting into the community. And if they're doing a lot of it, then they're connecting in very deeply into the community. So this brings us back to Rokwire. And one of the things we do in Rokwire community is we have these community contributor badges. And so I've taken a measure of these for over the last year, and this is based on 21 contributors. And so each contributor earns some subset of these badges. And so it's for different activities. So it's like meeting attendee, publication, GitHub activity, and so forth. And so this is the distribution below of the number of contributors, or the number of badges awarded based on these badges, and these badge categories. So you can see that this is a log value. So you can see that the greatest number of badges have been awarded for meeting attendee. And then the next greatest is a conceptual or technical advance. Now, this is not surprising since our community is relatively recent and we're trying to build some capacity in our network. So we have these contributors who are attending meetings. Some are making conceptual and technical advances, and that includes things like developing documentation or building some definitions for future contributors. And so you can only earn one of these badge types per person, but you can see that by default there are many people engaging, say, in meeting attendance, but not as many people engaging in conceptual or technical advances, and so forth. So this is an example of our network, and it's plotted out using Gephi. And you can see that there's a full community network, and it looks pretty deeply connected, in this hierarchical fashion. But it's not entirely the case, because the community manager is actually doing a lot of things in tandem with the contributors. And so in some cases, the community manager is doing some intense collaboration with the contributors. As you can see here at the right, there was only a subset of people where they've gotten at least 3 contributor badges, meaning that they're really involved in the community, or that they collaborate closely with the community manager. So there's this sort of hierarchical structure, but there's also this sort of one-on-one, and I wouldn't say it's hierarchical structure, but it's definitely more focused than some of the other activity in the network. And so this is the full contributor network without the community manager, to show sort of the difference in terms of the structure. So it's a little bit more clustered in this case, but the network statistics, which I'm not reporting here, are different in a number of ways. And then you have, again, this network of where you have at least 2 contributor badges in common without the community manager. So you see that there's a small subset of people work very closely with the community manager. But there also is a pretty decent group of people who share 2 or more activities. And so this means that they're doing the same types of things, but they may not be doing it in the same groups or at the same time. So this is that reconfigurability of expertise again, where we can switch people in and out. And we know kind of that there are a lot of people in the network that are doing certain things, and we can look at that distribution, that degree distribution that I showed you before, to show that there's this configurability of expertise that's built into this network. So now I want to switch to the OpenWorm Foundation, and so this is on a much bigger group of contributors, 228 contributors over 4 years. And this shows that if you look at, say, the Slack channels or the Slack team, you can actually get a degree distribution from that as well. So one of the things you can do is look at the messages that are sent on Slack, the number of messages, and then look at the roles of the people who are sending these messages to see if there's a long tail of contributors. And indeed there is, but this long tail consists mostly of specialized roles in the community. So in OpenWorm we have specialized roles. We have people who are just run-of-the-mill, contributors, but we also have people who are major collaborators, like they're from a major lab. They do a lot of collaboration. We have senior contributors who have done a lot of work in the past. We have Google Summer of Code students, and we have board members, and all those people in these specialized categories consist of this tail. So that's not surprising that that's the case. So that does show a little bit more hierarchy in the OpenWorm Foundation case, but it's not necessarily a hierarchy, because it just seems like they're doing more engaging with the community. It doesn't mean that they're working above people or that they're directing a lot of people. Although if you're leading a project, by default, you're sort of doing this. So another thing we notice about these networks is that we propose that there's a multi-level network topology at work. So one of the things that in the Orthogonal Lab, and that's also been replicated in the Rokwire community, is that you have these multi-level network topologies. So the first thing you have is an onboarding network. So you have a small number of curators, like the lab manager, or the head scientist, or the senior contributor, and they connect everyone to the community initially. Now, they may diversify afterwards, but this is where the initial point of contact comes. Then you have a collaborator graph, so that's different. This is once you're onboarded, then you start to collaborate. And the Slack team might be an indicator, or the GitHub repo might be an indicator. So who's forking and issuing pull requests in GitHub, or who's interacting in Slack? And these allow for selective crossover between teams, And this is another part of the graph. But then the third part of the graph is a participation graph. And this is where people collaborate via meetings synchronously and asynchronously. So they contribute to in-meeting discussions, contribute through YouTube or chat, and they can do these, they can mix it up as well in the participation graph. The difference between collaborators and participation would be I can participate in something maybe, in an ad hoc fashion, whereas a collaborator has a deeper tie to one another. So these are all three different types of networks that we can look at, or three different types of connectivity is maybe a better way to put it. So here are the sort of the squares that define them, and you can see that they're overlapping. This is a conceptual diagram showing that there's two and threefold overlapping. And then finally, there's this point about selective disconnectivity and intentional interconnectivity. Now these are key, but these are also quantitatively elusive factors in network evolution. So one way we can look at this is by going back to the OpenWorm Foundation and look at the units of contribution over time. And so this is a metric that I came up with here based on the dependency graphs on GitHub. So this is a dependency graph in the OpenWorm repository in the OpenWorm organization. And you can see that the dependency graph has the OpenWorm repo and then some of the other repos that have forked OpenWorm. And so there are all these different commits and other changes that are being made over time. So you can look at this small period of time and you can actually draw out this graph. And I made this very simple so that we can follow through what's going on here. So the edge that's labeled 1, that represents a generic change. This is contributed by 2 contributors and then merged by a third. The edge labeled number 2 is a Docker file that's being created, and this is being contributed by contributed by 1 contributor and then merged by another contributor. And the edge with 3 on it is a cloned repository by a single contributor, and then number 4 is a single thing that's forked by a separate contributor. So you can see how these contributors are doing their own thing, but they form this interaction graph. So they're contributing in this way, and you can see the network is sort of defining different nodes which represent different categories, these lines. So these lines are colored as the nodes, and those lines or those forks then are connected, either highly connected or not highly connected, and we can do an analysis like that. Finally, this selective disconnection with intentional interconnectivity, it goes back to the reconfigurability of expertise, which, if we recall, is this flexibility in membership between different modules in the network over time. We can look at different statistics to sort of quantify this, and one way we can do this as an alternative to network statistics is to use soft or fuzzy classification to look at clique membership per unit time. So this is sort of going back to the second OpenWorm example I showed you. So you can see that you have these 3 different cliques, and they have a membership function between them, each node. And then finally, we have this network robustness assessment, which is to assess the robustness of any given network. And so I'm going to talk about a general network here. I'm going to talk about the number of nodes in the largest connected component versus the number of edges removed. And there are actually 2 insights we can draw from this. This is a sort of a theoretical model of a robustness assessment, but it's basically based on the examples that we've seen. So if selected connectivity is too limited, we replicate the structures of a traditional academic organization. In other words, we get siloed sub-projects, and that's actually something we don't necessarily see in our examples, but to think of those networks as they evolve, if we have too much selective connectivity, that's what will happen. So people will yoke themselves to a single community manager or a project leader or connect to the most popular contributors. But if the selective connectivity fluctuates too much at long time scales, if there's too much shuffling in the network robustness hits a critical lower bound. And this risks community collapse or community discohesion, if you want to say that. So an example of that would be too many people withdrawing from interactions for months or years at a time. So in some of our communities, we have that problem where people go away for a while, and then they stay away because they're not being engaged. So this is the risk that you run if you have too much of that going on in your network. You simply just run out of people and the network collapses. So thank you for your attention. I hope that was informative. If you want to join one of our 3 communities, you can join the Rokwire community using the launch pass at the top, the Open Worm Foundation with the launch pass in the middle, and the Orthogonal Lab with the launch pass at the bottom. And they're all going to connect you to our Slack teams. And so there you can start participating in the network, learn about what's going on in the inside, and perhaps become a node in this network. Thank you.